Okay, now that we have discussed many of the pathways by which energy could be produced, we could actually summarize them here. So, the letters here, I would indicate what they are. G stands for glycolysis. Pre-TCA stands for the step before the tricarboxylic acid cycle. In short, that is actually the conversion of pyruvic acid to acetyl coenzyme A. And then TCA obviously stands for the TCA cycle. PBO stands for the pre-beta oxidation phase, the one wherein the fatty acyl-CoA goes inside the mitochondrion. BOC means beta oxidation cycle 1 and beta oxidation cycle 2. And we will discuss these terms here because they have something to do with the ATPs being produced along the way. So let's take a review. I'll take my colorful charts back with me. So let's go first with glycolysis. Alright? In step number 1 for glycolysis, we used 1 ATP. That's why here we have G1. And we resulted minus to minus 1 ATP. And then in step number 3, also another reduction of an ATP. So that's it for the energy investment phase. Now, for the energy payoff phase, we have steps 6, 7, and 10. So in 6, we have NADH plus 1 NADH, or in the case of a starting point of glucose, that's 2. Then in step number 7, ATP. Then in step number 10, another ATP. If you have 2 moles of GTP, that's 2 ATPs. And if we have NADH here, we would translate that to how many ATPs? That's 2.5, right? So it's either plus 2.5 ATP or plus 5 ATP. Alright. So when we summarize glycolysis, that's minus 2 here. That's what color do I use? Minus 2 ATP at the start. Then you assume everything else is double, so we use plus 5, plus 2, and plus 2. So 5 plus 2 equals 7, plus 2 equals 9, minus 2 equals 7. So you assume that there is 7 ATP produced net already, including this investment in each glycolytic cycle for every glucose, I mean. But there are shuttles that actually facilitate transfer of this NADH. Remember that glycolysis is performed in the cytosol, but NADH produced in the cytosol cannot be converted to ATP unless it goes to the mitochondria, because the electron transport chain is in the mitochondria. Alright, let me draw it for you. So we have NADH here. Let's say that this is the mitochondrion and this is the cytosol. NADH must go inside the mitochondrion because in the mitochondrion, the electron transport chain will convert NADH to ATP. If the NADH cannot go inside the mitochondrion, it cannot be converted to ATP. It's that simple. But there are 2 shuttles by which NADH can enter the mitochondrion. First is the malate aspartate shuttle, and this is a beneficial shuttle because it requires no ATP. However, in the glycerol phosphate shuttle, it would require 2 ATP from the NADH in order for it to come. It's as if it's a jeepney requiring a particular fare from the NADH in order for it to get inside the mitochondrion. Alright? So in cases that we have glycolysis in the glycerol phosphate shuttle, we would have 7 minus 2 equals 5 net ATP. Again, this is in the glycerol phosphate shuttle. But in the malate aspartate shuttle, we retain the 7 ATP. So that's it for glycolysis. Now, for the pre-TCA, again, I said that the conversion, this is the conversion of pyruvic acid to acetyl coenzyme A. And let me get that here. And this is that reaction from pyruvic acid to acetyl-CoA. We produced 1 mole of NADH. Alright, we produced 1 mole of NADH. So if we produced 1 mole of NADH, we assume that it would now produce 2.5 ATP. Is there a shuttle for this? The answer is no. Why? Because the Krebs cycle already occurs inside the mitochondrion, not outside. So you don't need shuttles for any NADH or FADH other than for glycolysis. Alright? So that's it. Now for TCA, the TCA yield, let's go back to the colorful TCA cycle here. So the first energy producing step here is step number 3. We have 1 NADH. Let's draw that here. Then in step number 4, another NADH. Then in step number 5, GTP. Step number 6, this one, FADH. Step number 8 is NADH. So if we convert that, alright, if we convert that, it's all 2.5, 2.5, GTP is equivalent to 1, FADH 1.5, and another 2.5. Alright. So meaning, for every acetyl-CoA enzyme, for every time an acetyl-CoA enzyme undergoes the tricarboxylic acid cycle, how many do we get? 2.5 plus 2.5 is 5, plus 1 is 6, plus 1.5 is 7.5, and 7.5 plus 2.5 equals 10. So you have 7 ATP per acetyl-CoA enzyme A. And that is not yet including the step before the tricarboxylic acid cycle, which is an additional 2.5 ATP. Now, if we're going to calculate everything starting from glucose, and considering that we are in the malate aspartate shuttle, how many do we have? So from glycolysis, we have 7. Again, this is malate aspartate shuttle. From the pre-TCA, how many do we have? This is only for 1 molecule of acetyl-CoA enzyme, right? But we produce 2 acetyl-CoA enzyme molecules from glycolysis. So this is 2.5 times 2 equals 5. And here we have TCA, 10 per acetyl-CoA enzyme A. Again, we have 2 molecules of acetyl-CoA enzyme A for each molecule of glucose. So that's 10 times 2 equals 20. So 7 plus 5 is equal to 12 plus 20 equals 32 ATP per glucose. If you use the malate glycerophosphate, then that's 30 ATP per glucose if they use the glycerol phosphate shuttle. Alright, calculation is that simple. Now, when we go to beta oxidation now, the pre-beta oxidation, recall whatever the case, regardless of how long the fatty acid is, because it requires fatty acyl-CoA synthetase, it would require minus 2 ATP. So it would require 2 moles of ATP. Now, for beta oxidation 1, phase 1, we have FADH again. And for 2, step number 2 gives us NADH. So, again, this would lead us to 1.5 and then 2.5. So, for every cycle, we have 4 ATP per cycle. But remember that in every cycle, we yield 1 acetyl-CoA enzyme A. So if 1 acetyl-CoA enzyme A yields 10, each cycle is supposed to give us a total of 14 per cycle. Alright? But then again, the net would be reduced by 2 due to this. So that's a total of 12 per cycle plus 8 acetyl-CoA enzyme A. Alright? So you can play with the numbers all you want, but the values are already listed down. Now there are 2 other factors, glycogenolysis and fermentation. In glycogenolysis, as the name implies, there is lysis or breakdown of the glycogen. And glycogen